Ever wondered how a transactional database actually works under the hood? We're going to demystify that whole concept by building a simple one, right here from the ground up, so you can see exactly how the magic happens.
All right, let's dive in. Here's our roadmap for this explainer. We're going to start with the absolute basics, then we'll add the power of transactions. After that, we'll uncover the secret sauce that makes it all possible, see how it looks in actual code, and finally, we'll put on our senior engineer hat and talk about real-world trade-offs.
First things first, let's build the simplest database you can possibly imagine. No fancy features, just a place to store and get information fast.
So the foundation for our entire system is this simple analogy, a digital notebook. Each page has a name, that's the key, and it holds one piece of info, the value. The beauty is you don't have to scan the whole book, you just flip straight to the page you need. And in the Go programming language, this concept is just beautifully simple. It's implemented with a basic map. This data structure is incredibly efficient for our notebook, letting us find any page almost instantly.
Our notebook really only does three things. Set lets you write a value on a page. Get lets you read what's on that page, and unset, well, it rips the page right out, like it was never there. These actions are super direct, super immediate. But what happens when we need to group them together and, maybe change our minds?
This is where our simple little notebook gets superpowers. We're going to introduce the idea of transactions, which give us the ability to try out a whole group of changes and then undo them all if something goes wrong. The core idea here is a try mode. Think of it like editing a document where none of your changes are final yet. You're keeping a separate list of undo notes on the side, and until you hit save, you can revert everything back to how it was. And this slide right here, it shows you the why perfectly. On the left, without transactions, if an error happens midway through, our database is left in a corrupted, inconsistent state. But on the right, with transactions, that rollback command just erases everything we did. This is a concept called atomicity. Either all the changes succeed, or none of them do. Okay, that makes sense for one level, but real-world scenarios are often way more complex. You might need to start a try mode inside another try mode. So let's visualize how these nested transactions actually work. Okay, imagine we're working on a whiteboard. First, we begin a transaction. Let's call it T1. And we write A equals 10. Then, inside that same session, we begin another nested transaction, T2, and we update A to 20. Right now, the current state on the whiteboard is A equals 20. Now a rollback command is issued, and watch what happens. It doesn't undo everything. Nope, it only undoes the most recent, the inner transaction, T2. It's like erasing just the last thing we wrote. The value of A snaps back to 10, which is the state it was in right before T2 started. Then, if a second rollback command comes in, that's when the outer transaction, T1, gets undone. This erases the A equals 10 update, and now A is back to its original state before we even started, which was nothing, or null. Each rollback just peels back one layer at a time. So how do we actually build this rollback magic? It seems pretty complex, right? Well, the secret is a simple but really powerful data structure, the undo log. Here's the core idea, the whole secret right here. Before we ever change a value in our main notebook, we first write down its old value on an undo note. Then we drop that note into a box for our current transaction. And what's really crucial is that the main notebook gets updated immediately. That's what keeps our read operations so blazing fast. So this three-step process is the engine that drives our whole system. When we set a value inside a transaction, first, we look up what the old value is. Second, we record that old state in our undo log. And only then, third, do we apply the new value to the main store. We literally save the past before we create the future. All right, we've covered the concepts and the analogies. Now let's see how these ideas translate directly into clean, effective Go code. And would you believe it? Our entire database structure is defined by just these two fields. It's so elegant in its simplicity. Let's break down exactly what each one does. First, we've got the store. This map is our single source of truth. It's the whiteboard everyone reads from. This design is why our get operations are so fast. Then we have TX stack, which is literally a stack of those transaction boxes we talked about. Every time we call begin, we just push a new empty box onto the top of this stack, ready to hold our undo notes. And here it is. This is where the magic really happens, inside the rollback function. Now, this code snippet might look a little dense at first, but its logic is a direct implementation of everything we've just discussed. Let's break it down step by step.
The process is very specific. First, we grab the topmost box of undo notes right off our stack. Second, and this is the absolute key, we loop through those notes in reverse order. For each note, we restore the key to whatever state that note describes. That might mean setting its old value or deleting it completely if it was brand new. Undoing the last change first is absolutely essential.
So this design is clever, it's simple, and it works perfectly for the challenge it was designed for. But now, it's time for a reality check. Would a senior engineer ever approve this for a real production system? The short and honest answer is no. And understanding why is just as important as understanding how the code works. It all boils down to the specific trade-offs we made in our design. This table really illustrates those trade-offs perfectly. By keeping everything in memory, we get extremely fast reads. That's the advantage. But the pitfall? Zero durability. If the process crashes, all our data vanishes. By updating the store immediately, we make a commit essentially free. But a rollback on a massive transaction could be painfully slow. And finally, a long-running transaction could eat up a huge amount of memory, storing all those undo notes. Real databases solve this durability problem with techniques like write-ahead logging. And that really is the final takeaway here. Every system design is a series of trade-offs. There's no single right answer, only the best answer for a specific set of problems. Our design optimized for fast reads, so I'll leave you with this question. How would you design it differently if you needed rollbacks to be instant? Thank you for joining this explainer.